Hi, I'm Mark Weitzman. Welcome back to Quantum Field Theory, a student's perspective. In this deep dive, I want to talk about the transformation of a W boson, which is a spin 1 particle of mass m, non-zero mass. We're going to talk about a single particle state and see how it transforms under Lorentz transformations. This problem is problem 1 in chapter 2 of Weinberg's first volume of his 3-volume treatise on quantum field theory. I'm treating this now because even though we haven't gotten to spin 1 yet, and we won't get to spin 1 for quite a while, I want to show you that quantum field theory really is just relativity and quantum mechanics, and that using what we know about non-relativistic quantum mechanics and spin, and what we know about relativity in terms of transformation of coordinate systems, we can solve this problem. So let me draw a diagram just to make clear what's going on. You have a z-axis, y-axis, and an x-axis. And this is the origin, and I'll call this O, because this is the observer O's reference frame. Now what we have in this frame is we have a W particle, W, and it's traveling with momentum in the y direction. So it's got an absolute value of momentum, let's just call it absolute value of P, and it's got a sigma z component, the spin component, which I'll talk about in a second, equal to sigma. Sigma could be like plus or minus 1 or 0, or it could be a superposition. So this is the setup for how O sees the problem. Now, O also sees another observer, it's called, who's moving with velocity v, call it O prime, in the z direction. And so O sees W boson with spin 1, mass m, unequal to 0, single particle state, with momentum P y. It's the only component that's non-zero, and it has a spin z component, as I said, sigma. O prime moves in the z direction with velocity v. And the problem is, how does O prime describe the W boson particle state? I'm sort of being meticulous here in the problem definition, but anytime you do these transformations, it can get a little bit tricky and everything. So I want to start with a preliminary analysis. First is what I observed earlier. Quantum mechanics and special relativity can solve this problem. Qm will be graded in the reference frame of the particle, in the rest frame, not the rest frame of the particle. And SR takes care of whatever whatever boost we need. Notice, let me go back to this. This means we know how to deal with rotations. And you know, in your ordinary quantum mechanics course, usually you do spin 1/2, and sometimes, and many times you do spin 1 as well. And we'll talk later how a spin 1 transforms under a rotation. Many of you know that a spin 1 particle is essentially a vector particle. So it transforms very easily. It transforms just like a vector. And we'll use that later. But, so this is why we can solve the problem. Now, the second thing is, it's not that trivial to define the spin state of a moving particle. The reason is that the orbital and spin parts of the angular momentum they get entangled. So for instance, in this problem here, we think we know what the spin thing is, it's in the z direction, but there also is orbital angular momentum in the z direction, because the orbital angular momentum in the d direction, we don't know that x equals 0. Since we know the momentum in the y direction, the x component and z components are 0. Px equals 0, Pz equals 0. That means we know nothing about, by the uncertainty principle, we know nothing about x or about z. So it could have an x, and it has a py. So xpy is orbital, is Lz. I leave out the other part minus the y px because px is 0. So it has spin and it has orbital, and they sort of get entangled relativistically. The separation isn't as clean as in non-relativistic quantum mechanics. So how do we solve this problem? Very easily. We define the spin in the moving reference frame as simply the spin in the particle's rest frame. In other words, what we're saying is, if we have a particle at rest and it's got spin, this is a semi-classical argument. I can make it more rigorous, but I'll just give a semi-classical argument. So imagine the particle's at rest. I'm drawing a different picture than here. I just want to work in the z direction. X, y, z. The particle's just at rest. But we could think of it as a little ball that's like spinning. Okay? So its spin component, as z classically, would be some kind of sum of r cross p z, where, you know, it's moving on the outer edge, so it has some p. And this is equal to the sum of xpy minus ypx. Now, in the boosted frame, look at a boosted frame where we have x prime, y prime, z prime, and the particle is moving velocity v. It's also spinning, but it's moving. In this frame, we could calculate the spin things, and we would get the sum of x prime py prime minus y prime px prime. But these are the same, because under a boost, in special relativity, transverse components don't change. So x and y are transverse. We're boosting in the z direction. X and y don't change, and momentum is also a 4 vector. Py and px don't change. Pz changes and z changes, but transverse components don't change. So this gives us good reinforcement that when we boost the particle's spin to a new reference frame, it doesn't change. Now, what if it's transverse? You know, what if the spin is like in this direction, and then we boost it in this direction? Does the same argument doesn't seem like it applies. Well, here we can just use quantum mechanics and say that a transverse state, or any state, will be something like A plus 1, where that's the spin in the z direction, plus B times 0, plus C times minus 1. And now, when we boost it in the z direction, all of these states don't change. Quantum mechanics is linear, so the state's going to be the same. It's going to be A times plus 1, plus B times 0, plus C times minus 1, and that's just going to be equal to S. So our spin states don't change under a boost. And Weinberg in his book just defines the spin state of a moving particle as being the spin in its reference frame, the rest frame, and we boost it to the moving frame. So in the next few videos, I'll go into detailed calculations about how to calculate the actual W boson particle state. But I just wanted to do some preliminary analysis to get our bearings, because this is an unfamiliar topic. Thank you very much. I'll see you in the next video.